Okay, line J1, identify components of distribution centers over here. In J1, this line there, this learning task over here is going to be without pictures because really it's just a lot of text and explanation. We're going to go over top of a couple of different components and approaches that we're going to go and utilize while selecting some of this. And we'll go through a couple of calculations as we do as well. The first thing we're going to talk about is overcurrent and overload protection. And the CEC does require that there's going to be overcurrent and overload protection. That is going to be for every piece of equipment, as well as every time that we step down from a larger value to a smaller value of equipment. We're going to have to go and have overcurrent protection that we're going to go and have protecting our entire installation. Then that's going to go from there. If we feed off to other pieces, we are going to need to go and overcurrent protect every time that we downsize. And we're pretty used to this because anytime that we're putting stuff into a panel, we're taking stuff off on a 15 amp breaker out of a 100 amp or a 200 amp or whatever the size of panel is that you're working out of. We're used to putting this stuff in here for the bulk of our components. However, if we're talking about things like splitters, which are part of our distribution, a splitter is not considered to be an extension of our actual main panels. 2 seconds. I don't know what's going on here. Let's take a look at what that actually goes and means. If we take a look at a panel box over here, we are going to go and have feeding into this panel box. The first thing that we're going to do, we're just going to draw it as a one line, is we're going to feed into our main circuit breaker that's inside of there, and then from there we feed out to every other type of load that we are going to go and distribute out of this thing. We'll have different overcurrents that are going to be placed inside of here based upon the types of loads that we are feeding out. The panel breaker itself, which is this component over here, is designed to go and protect the actual panel bus bars, which are the components that go between the actual breaker and out to the individual loads themselves. What it is not designed to do is it's not designed for us to go into here and say, well, we've got a splitter, we've got, maybe a 200 amp panel over here, and I'm going to come out of that 200 amp panel and I'm actually just going to directly connect the lines from my splitter onto these bus bars themselves. That'd be the same bus bar, that doesn't even make sense. You're not allowed to go and do that where you tap directly off of the buses. You need to go and have a separate overcurrent device that's going to go and run off of it from here into that. So it's going to be protected through this breaker right over here into that actual splitter that we're going to go and have. Fusible disconnects are sometimes used instead of combination panel boards, where we're going to come into a service and we're going to go through that fusible disconnect. Comes in, it enters into a set of lugs, we got that switch, and then we are going to go and have that actual fuse section that's going to be there. This is all going to be inside of one main assembly. Fusible disconnects come in our three-phase standard values of voltage and current. They're going to go and have neutral blocks that are sometimes going to be included with them. A lot of cases, three-phase fusible disconnects don't come with your neutral block, and if you have a 4-wire or a Y-type, you need to go and order that one separate. That gives the ability to go and, once again, drop down and protect something that's going to be downstream. So if I take a fusible disconnect, I can use that fusible disconnect to protect any type of a load or splitter that's going to be further downstream. Overcurrent protection needs to be done properly through all of our three-phase systems. And what we mean by properly is that we need to be able to interrupt the total amount of fault current that we are going to go and have. If we have got a large installation, so we're going to give a value here of a 500 kVA transformer that we are using to go and feed out to a 120 208 volt secondary. So we use our transformer, and on our secondary, it doesn't matter what the primary is, but it's a 120 208. You should be able to go and recognize that the 208 is your line value of voltage, the 120 is going to be your phase value of voltage, and what we can do from this is we can figure out our total amount of line current that we would have going out of this. Let's go and do that. That's going to be a matter of VA divided by E line times root 3 over here. Going into our calculator over here, 500,000 divided by, make sure you put those brackets in, E line, that's our line voltage, times root 3. Bracket and done. And we see that we get a total current out of this thing that is going to be 1,387. So that's the total amount of power that we could carry out of it. our total amount of current, not power, 1,387 amps that we can carry out of it. Now, every transformer is going to go and have a percent Z that's going to be labeled on it. And this is our percent impedance, which is going to be something we divide our line current by. If this one over here has got the label of being 3.5%, that means that we are going to go and take this value of current over here, my I line, divided by my percent Z is going to go and equal my I fault. This is a common formula that you should have memorized at this point. Let's go and take a look at that. We're going to take this I line, 1,387 that we have over here. Put that better into there. 1,387. I'm just going to divide it by 3.5%. So divide by 0.035, right? This is 3.5% out of 100 here. Equals a total value of 39,653 amps. That means that during a fault, a bolted fault, what we would call a line-to-line, where I'm just going to cross, my lines over here, this transformer is going to be able to go and put out for a short amount of time 39,653 amps. That's a phenomenal amount of current. Now, this current needs to be interrupted by whatever I've got for my overcurrent protection that I'm going to go and have. So that means every breaker, because even if I go all the way downstream from my transformer, I then go into some other distribution, and from there I go further downstream into other sub-distribution, from there into other sub-distribution, I could be all the way down over here where I've got a 3-pole 15 amp breaker over here. This 3-pole 15 amp breaker, I could go and short across all 3 lines, and if I do so, then it is going to be able to go and create that short circuit at this 500 kVA, and that 500 kVA is going to try to deliver this all the way out to there. Now, we'll never be able to hit that absolute maximum because there is going to be reactances and resistances that are going to be caused by my lines ahead of it. But we don't really care what those small amounts of losses are. What we know is that we have the potential that if my reactances and resistances were not there, that I could have a total of that amount of current that this 15 amp breaker over here would have to interrupt. Probably not going to happen inside of most cases. If we have this transformer over here, we've got 3 main approaches that we can go and use for our fault current or for our overcurrent calculations based on that fault current. So I'm just going to take this one over here. First one that we could do is that every single place that we have got a breaker or a fuse, that we would make sure that that breaker or that fuse is going to go and be able to go and interrupt 39, we're just going to round this thing, 40 kilo amps that we'll be able to interrupt. This is going to be unlikely for breakers to be able to go and open 40 kilo amps. It's going to be unlikely unless we go to some really large frame type of breakers over here. Even if you could create this type of a system, it is going to be incredibly costly. Lots and lots of money that's going to be spent on trying to go and deal with this transformer's 40 kiloamps of fault current that we would want to have. So, since that one doesn't work, let's take a look at our next option over here. Our next option would be what we would refer to as a fully rated but coordinated system. And what that means is that we're going to go and have shorter and shorter amounts of time. Each of these still has to be able to interrupt this 40 kiloamps, but rather than them all having roughly the same time to go and respond, whatever is furthest downstream is going to be fastest, and whatever is furthest upstream is going to be slowest. I'll write that over there. Which means that if I'm taking a look at a fault, whatever is going to be fastest, the device that's furthest downstream to where the actual fault itself happens, let's pretend that our fault happens right over here, that would mean that since this device over here has the fastest response, it would be the one that would go and open. It still has to interrupt the whole 40 kiloamps that I'm going to go and have over here, but it's going to go and do so fastest, which means that the rest of my installation, all of this over here, is still going to be able to maintain operation. In our first one that we looked at, where we just said they all have to be able to interrupt it, but we didn't coordinate them, there would be issues because it could be that, this one over here would be the first one that would open. And if that would open first, it's going to kill the rest of the system, and we're going to have a hard time tracking that down because we're going to have to go through every branch of all of my distribution to try and sort out where that fault itself actually was. The third approach, which is going to be the best approach and the properly designed approach, would be for me to go and use what we're going to refer to as a series-rated coordinated system, or series-rated combination type of protection. And this just means that I need to have at least one thing in my circuit that is going to be able to go and interrupt that 40 kiloamps of fault current that I'm going to go and have. So my very first piece of protection inside of here is going to be rated for my 40 kiloamps over here. And then I'm going to go from there down into my next bit of distribution. We'll just draw out another little bit of distribution. From there, I'll go down into another layer of distribution. Each one of these could be, distribution centers or individual panels, etc. But as I do so, what I'm going to do is I'm going to go and continuously drop the kiloamp rating, the interrupting rating that I'm going to need to be able to go and clear. And we do this for, this main reason here. Ultimately, whatever fault current we have will be able to be cleared by the system. That's the main thing that we need to keep in mind, is because our very first one is going to be rated for whatever I've got for my full rated fault current. We know that we have got a system that will clear a fault. But then what I'm going to do is I'm going to drop down in my total amount of kiloamps as I go through the system over here. This one over here is going to be rated for 30 kiloamps interrupting. And then this one over here is going to be rated for, maybe 20 kiloamps of interrupting. And this one down here, we're going to go and bring that one down to 10 kiloamps of interrupting. As we're getting through smaller and smaller frames of breakers, we see just smaller and smaller amounts of kiloamps that we are going to be able to interrupt. And what we're going to need to do with these is we are going to need to go and coordinate the overcurrent protection, so that if I have got a fault that is 40 kiloamps, which breaker would I want it to go and open up? If I do actually end up with a voltage fault, do I want this breaker, this breaker, or this breaker to open up? Obviously not. This one's going to be destroyed. Same with this one's going to be destroyed. Same with this one's going to be destroyed. Which means that if I've got a really, really high amount of current, the one I want to go and respond fastest would be that if it reaches that level. However, I want this one here to be fastest at 40. Fastest at 40. But I want this thing to be slowest at 10. And the reason that I want it to be slowest at 10 is because if I'm all the way down here at 10 kiloamps, it's still going to go and interrupt 10 kiloamps. But if I've got a fault all the way down over here that is only going to be a 10 kiloamp fault, I would want this thing then to go and trip this breaker. I'd want this breaker to be the fastest at, let me just break that out, 10. And the slowest at 40 kiloamps over here. So what we do is we basically go and rate these things from the top down, but we won't do it. It's going to be done by the manufacturer, but they're going to rate them from the top down, saying your first one has to be able to interrupt the total amount of fault current. It's going to be an engineered solution, and it is going to be the fastest at that large amount of current, but it's going to be the slowest when it comes to small amounts of current. Basically, the larger the current, the faster it's going to go and operate. This one down here is going to be the slowest when it comes to 40 kiloamps, but it's going to be the fastest when it comes to a 10 kiloamp fault alone. Which means that if I fault the system out right down over here, this one over here is going to be the one that will trip. And as soon as it trips, then it's going to go and leave the rest of my installation, all these other feeders, etc., still operational. Anytime that we have got a series-rated combination, first of all, we don't go and build this ourselves. This is going to be, we will put it together, but we're not going to go and design this ourselves. This is going to be put together by an engineering firm that's going to go and spec it. They don't really put it together. They just read the tables and say, this is the system that you need to go and have, and they sign off that it's going to be safe. Anytime that we do have these, what we need to have is we need to have markings on all of our equipment that it is going to be part of a series-rated combination. We need to go and mark that these are all part of a series-rated combination. And then we need to know what the total series rating is going to go and be. In this case, it's going to be a 40 kiloamp series rating, as well as I'm going to need to have markings that are going to indicate that, look, if you take this breaker out, you have to put the exact same type of breaker back in so we can maintain this series rating. Okay, that covers us off for that. Next thing we're going to talk about is just going to be bus bars. Bus bars are going to be those long, silvery-looking bars you see inside of distribution equipment. And we took a look at some of those when we were looking at the MCC. We saw those bus bars on the horizontal and vertical sections. They're going to be made of conductive materials such as aluminum or copper. Now, because aluminum does oxidize and copper oxidizes as well, we're usually going to go and flash them, which means that we're going to place another thin layer of metal over top that does not corrode. Tin is an excellent one. Think about nickels and dimes. Those things are coated in tin. You stick them in your pocket. Those things don't corrode, even though it's, salty and moist and warm inside of that thing. Tin's great for protecting against corrosion. So you can go and use this, as a coating over top. Sometimes where we need higher conductivity, we will use silver, but silver does tarnish, which also leads to resistance off it, as well as it's just more expensive. So typically, we're going to go and see tin-plated aluminum or tin-plated copper. You're not going to have a solid bar all the way through, except on some older pieces of equipment. Bus bars are oftentimes going to be built by the manufacturer as being a single component that we are going to go and have, meaning that if my manufacturer builds out a panel, it's going to have a couple main buses that go down the back. They don't want to have tons of different sizes, so what they'll do is they'll say, up to my 200 amp frame, we're going to use the same bus bars across the top over here, and really just the main breaker that we go and bolt in up top here is going to be the part that we change. So, a 125 amp main is going to be able to bolt on there, same with a 150 amp main, same with my 200 amp main. It just saves on manufacturing costs. What you do have to do with any time that you have got bus bars is that any sort of a bus bar connection where you're going through from one piece of equipment to another. This is very common inside of larger pieces of industrial equipment. Let me just sketch one out here real quick. Large pieces of industrial equipment are oftentimes going to come as segments. These segments are usually going to be under 36 inches wide because we have to fit them through doorways to get them into electrical rooms, etc. There's nothing worse than when you've got a large piece of equipment and it gets placed into the wrong electrical room, and then you can't get this thing back out. You have to disassemble it. So usually they break them apart into these smaller 36-inch sections that you're then able to go and carry in to your electrical room. And what you're going to have inside of there is you're going to have a series of bus bars. We're going to have a bus bar that goes across the top of each one of these here, red, black, and my blue phase over here. And when I go and carry these things in to here, what I'm going to have to do once I've got them placed is I'm going to have to go and make connections. So there's going to be specialized plates that come from the manufacturer that are going to go and span each of these gaps here to go and carry any sort of power that we need to through our system itself. When I place these in, they're usually going to be done with a bolted type of connection that's just going to go and bolt through from one to the other. If we don't have torque specs, and there should be torque specs off of there, but if we don't have torque specs, you're going to go to the Canadian Electrical Code, and Appendix D has tables D6 and D7. That's going to go and give you some recommended tightening torques. The other thing about bus bars is when we are tightening them together, we need to go and have some way to make sure that these things are going to be able to withstand any sort of thermal irregularities. In other words, as my service heats up, I'm going to go and have expansion because almost everything has got a positive temperature coefficient of expansion, which means that my bolts that are going through here, I'm just going to go and draw a bolt down through here. There's my bolt going all the way through this thing. Does need to go and have a little bit of slack that it's going to be able to go and move back and forth with. Because in a lot of cases, you're going to go and have these bus bars that are going to be dissimilar metals, aluminum, usually, and then you're going to go and have this, which is going to go and be steel type of bolt. And because they're going to expand at different rates, that means that this joint is going to get tighter and looser. The way that we deal with that is that we are going to go and place on either what's called a conical washer. That's a washer that is cupped like that, which means that as I go and tighten down my nut on this side over here to whatever the spec is, this is going to be always a little bit bowed. We never want to flatten them all the way down. If you flatten them all the way down, there's no point in having that conical spring washer, but this thing is going to be pressurized. That means that now as these bus bars go and expand and contract due to heat and current that we're flowing through there, there's always going to be pressure that's going to be applied by this conical spring washer. Sometimes we'll use split spring washers as well, but it's far more common for us to go and use those conical ones. They give you an example for a recommended torque, for 1/4 inch bolts, and they show you how to go and do it inside of the module on page 31. Power factor correction, we have talked about numerous times. We're just going to glass over it at this point over here. We know what our limits are going to be for power factor. We're usually looking for a 90% power factor or greater. We want our power factor usually to go and be greater than 90%, but we want to try and keep it below 95% if we can. Because if we accidentally take it above 100%, we end up with massive penalties that are going to be assessed by our power authority. All these smart meters at this point do track your kilowatts, kVA, and your bars. So BC Hydro knows instantly if you have got any sort of an issue. And where the issue really lies in is the fact that you might have your installation over here that you're in charge of wiring, but there might be a couple of other ones that are nearby. Okay, let's go with this one over here. You got a machine shop that you are wiring up. And then right over here, we got somebody that makes robots. Those sound expensive. And then right over here, we've got somebody that makes medical devices. Those also sound expensive. And what happens is all three of these could be fed off of the same pad-mounted transformer that's going to be feeding this industrial unit. So they come off of here, we come off of here, and they come off of there. And what could happen is you've got a crap power factor, and instead of properly sizing it, you just buy a crap ton of used, capacitors off of some surplus site. You place these all in, and as soon as you bring this to over a 100%, so 100+% power factor, what happens is my transformer that they're attached to, the voltage is going to go and rise. So my voltage now goes up. So now, because this is the transformer I'm connected to, it turns out they're also connected to it, their voltage is going to have risen, and their voltage is going to have risen as well. There's a very good chance that when we see a rise in voltage, we are going to go and see destruction. We'll just blow up some stuff here inside of the medical place and the robot place. Guess who is going to go and be responsible for that? BC Hydro tracks all of this stuff, which means they're going to have record. They're going to know exactly what happened. They're going to come to whoever owns this machine shop and say, hey, in October 2020 over there, all of a sudden you went to a leading capacitive load and we blew up a bunch of equipment, expensive equipment in the medical and robotics facilities next door. And the owner's going to say, I don't know anything about that, but you should talk to my electrician because he was here on the 20th, and it's going to come back to you. And BC Hydro, although they make a ton of money, they do not want to pay for anybody else's damages. They will come to you and they will chase down your company for any sort of the losses. They have no problem when these guys over here and these guys over here say, I've lost $20 million yesterday. They'll be like, that's fine. We'll pay out the $20 million and we'll take that money back from the guys that caused it. So they will just sue you in the machine shop together. It's going to be a very uncomfortable situation. So keep this power factor below that 100%. Environmental ratings of enclosures is another thing that's talked about inside of here, where they talk about my NEMA designations, as well as they are going to go and talk about my IP, or my ingress protection designation. CSA enclosure designations are going to be listed inside of the code book, and we're going to go and have, our type 1, type 3, type 3R, etc., but they're not the same as the NEMA ones. They're substantively the same, which means that they're very similar and cover basically the same things. But if something has a NEMA rating, we still can't use it unless it's got a CSA rating as well. And our IP ratings, excuse me, IP ratings are very commonly seen on stuff. A lot of times, if you're buying wet location fixtures, you're going to be looking for stuff that's going to be IP rated. And it's very common that we just kind of use that as a slang term right now. IP rating is going to be an IP with this ingress protection. Ingress means getting in this. Protection means how hard it is. And then there's going to be two spaces. The first space over here, or the first number, is going to be the level of physical, of components, physical protection that we have from actual things like dust and chips and sand and stuff like that. The second one is going to go and be my liquids that I'm going to go and have. There is a table inside of your code book all the way into section 18. Then there's a note that kicks you all the way over to your appendix B that gives you one of these tables. You're going to have to find that for some of this week's components that you're going to be looking at. But it is going to go and tell you how to go and classify your IPs. And they do give you an example as well underneath here on section 32. How do you go and use that IP table, go through that example, and then follow along inside of your code book.